projector isn't working. So I would recommend that if you're in the back, you might want to come closer because in terms of the chalk of this thing does not resolve very well. So, if I start writing here, you're not going to be able to see things as clearly from way in the back there. If you can, well and good. But if you can't, you might want to come a little bit closer today at least. Okay? Just a warning. Okay. Very well.
Camera is better.
Huh?
Yeah.
Camera likes the blackboard better?
No, it cannot read it properly. It's not very clear.
Okay.
Can you just turn off your autofocus and just manually focus it?
I'm doing that.
Okay. All right. So today I felt like, especially when we're covering LPs, these multiplicative weight updates and SDPs, things be getting a little intense, and maybe we need to sort of take a step back and sort of see if we're digesting everything at the appropriate rate. So, what I thought I'd do today, which I mentioned is a sort of free lecture, is not that we won't do anything at all, but what I would like to do is, as far as possible, keep this interactive, where I take questions possibly from you all about things we've covered so far, possibly even some project questions, although unless they're very general, I prefer to keep them for the office hours and other appointments I'm trying to schedule with you all. But so what I'd like to cover is our general questions about LPs, because we have another assignment that'll be due for LPs and SDPs maybe a little bit, and just thinking about these concepts, because these are very, very new concepts, things that you're very familiar with. And it'll be good to sort of, in this kind of format, just take some questions from you. I have things I can talk about. I was going to do a couple of examples of, again, how to construct an LP and what it looks like and what you can infer from it. And I can do that. And I will start with that if you like, but it's always better if I base what I want to do on questions that you all may have. And this is not, I know there's the usual, 10 people who ask all the questions, and there are others who may not be asking questions all the time, and this is a good time for those of you who don't normally ask questions in class to sort of clarify, I don't understand this thing in this lecture, can you explain this to me? I don't understand this, what you said here, can you explain this to me? This is a good time to do that here today, I think. So having said that, I'll give you a few minutes to think about if you have any questions, and if not, I can just start talking, which is infinitely less interesting. Any questions? You are one of the 10, but still I'll take your questions.
Just a logistics question. Will there be a homework after the LPs?
No.
So that'll be the last one?
That'll be the last one. So flows and then LPs will be done. Yeah. So, yeah. So questions? Or I could start asking people to answer questions, which would be much more harsh. Only to understand what I need to explain better, but, it's still, I prefer not to do that, So linear programming. Forget semi-definite programming for now. It's a little bit trickier. There's linear programming, duality. There's geometric polytopes and directions and all. So what's your take on all this stuff? Any questions about this? Yeah.
Could you, as concise as possible, go
No.
over what you do
Sorry, go ahead.
to tell that you should apply linear programming? What are the signs that would be a
Good.
good idea?
That's a good question. That's something that I've harped on before. What are the signs? The first thing you have to remember, and I've said this before, right, is that, so let's write down our standard integer program. Okay? And the thing that makes this an integer program, of course, is this constraint there are n variables. And of course, this could be instead z to the n. It could be any integer. It could be -1, 1 to the n. the exact form doesn't actually matter, as long as it's some integer set. And it's not a hard exercise to see that if you were allowed to do this, you could do this as well. It would not, you could reduce this problem to this problem and not change your complexity in any way. Okay? But in general, this is your integer program, right? It's got the linear constraints and the integer constraint here, which makes it an integer program, not a linear program, right? Okay. And so the question was, how do I know when I should apply linear programming? And the answer is in the fact that this problem, IP, for integer programming, is NP complete. Okay, so why does that answer the question? If integer programming is NP complete, yes, that's bad news, but it's also something else. What does that mean? I mean, what is that in just purely definitionally for problem is NP complete? Yeah, you want to say something?
Precision problem?
Pardon me?
Precision problem?
Well, okay, you're right. Let me rephrase. I should be more careful. Okay.
There is a reduction from the other NP.
Yes. And
I was gonna say.
so there's a reduction from any other NP-hard problem to this one, right? That means given any other problem, there is a way to make it look like this and try to solve it. So if your question is, when can I apply linear programming? The answer is, whenever you want. Because for any problem, there is a way to write it as an integer program. There's a way that you can just drop the integer constraints to get a linear program. You can solve the linear program, and now you can think about what to do with with your solution. Do you want to round it? Do you want to look at the dual and the prime? Do you want to play some games? You know, the various things you can do. So in general, if you have what is, say an intractable problem that's known to be NP complete, and you have no good way to start off in thinking about it, it's always a possibility that linear programming will give you something. And even if it doesn't, it'll give you some insight into the problem. So that's the answer to your question. Whenever you want, especially if it's intractable. So if you know the problem, right? So again, so the flow is, you take your problem that is intractable, you don't know what to do with. You don't have any idea where to start with it. You write it as an integer program, which you in principle can always do, but of course in practice you have to think about it. It's not always obvious how to do it, right? But there, you know there's a way to do it because it's guaranteed. And then you convert that to a linear program. You solve the linear program, so you get a solution. And somehow you have to find a way to make it integer, which will give you back the solution to you. So this is a very common flow in algorithm sort of design, where you try to go to the LP, figure out a solution, and try to get it back somehow. And of course, we've seen things like rounding. And there are many other ways. If you took a class on approximation algorithms, you will see that there are many, many ways in which you could think about going back. Now, this is not the only way you can try to solve a hard problem. But the question was, when might you try to use linear programming? And so it's a very good general purpose black box. Because the good thing is there's a lot of work, a ton of work, on how to do these kinds of reductions, how to solve these problems efficiently, and how to convert these things back. So you're able to get your problem into a space where there's been a huge amount of study. And there's definitely some hope that you can do something. And maybe you can relate your problem. Maybe your problem looks like something weird, but somehow you can convert it to, I don't know, something that looks like a max cut-ish problem. So we'll call it max cut-ish. Not quite max cut. And you say, okay, fine, I know to write an LP for max cut, so I'll write one. And then you can do the whole thing and then go back. So that once you have this big thing here, with a lot of power in it, it behooves you to try and somehow get into that frame, because then now you have weapons at your disposal. Okay. So that's one way to think about this. All right, good. That's a good question. So for those of you who have been trickling in, today was, my intention was to make today a kind of a free lecture, where we take some more interactivity, more questions and answers. I have things I can talk about that I will, but I would prefer to sort of have it be driven by the questions that you have, rather than what I think you ought to know, which is always a very different. Next question. Everything you want to know about LPs, but too afraid to ask. Yes.
Sorry, I'm just saying something. So TSP was also an LP. So, but we cannot reduce TSP to LP, right? Or no, so we could reduce TSP to IP, right?
Yes.
Oh, wait.
There is an integer program for TSP. Yes.
How difficult
are integer programs on average.
What does that mean?
Like, for example, SAT, you can solve pretty easily on average, just
What does that
there's
mean?
some cases that
No,
are
no, no,
hard.
what does that mean?
That means that most cases are easy.
What is most?
Uh,
There's a reason I'm being annoying.
no, that's.
There usually isn't, but today there's a reason I'm being annoying.
Okay. Well, one way to phrase it is, we can write algorithms that solve most of them, but that's
What's
a very
most?
good
No,
formula.
no, no, what's most?
Just one we use in practice.
How is that, what does that mean?
Okay, so if you want to talk about formally.
Yes.
Then what we mean is that the expected, so given a problem of size n, the expected runtime of some algorithm you can provide is polynomial in time.
Expectation with respect to what?
You can just do the size of the problem instance.
So the size of the problem is a random variable?
Well, with respect, yes, with respect to an algorithm.
So the size of the problem instance is a random variable?
No.
Oh, so in other words, what is the random variable that would be the expectation of it?
So you have your size, which is the size of x. Your random variable would be the constraints.
So the constraints are random?
Yeah.
Okay, so you're saying that I design an instance that's random and that the constraints are constructed randomly.
Yes.
Good. Now we have a fully specified question.
Okay.
So the question is the following. I have a family of instances of SAT. Let me see where I should write this down. So you want to solve SAT, and you have some instances, right? Some collection of instances, and you have a distribution over them. So you can pick an instance at random somehow, maybe by choosing the clauses at random. And now you're saying I pick an instance at random, and I have some algorithm that takes this input and runs in a certain amount of time and gives you the correct answer, right? And I want to compute. So let's say this is TAY, and I want to compute the expected value of this over this input, right? Okay, what's your question now?
So my question is, basically, is it possible to have the expected value be a polynomial amount of time for integer programs under this random variable? Do there exist algorithms that have an expected value of polynomial runtime?
Well, the trivial answer is yes, because my distribution is going to be a distribution only over the satisfiable instances and not the unsatisfiable ones. And so with my algorithm is yes.
Well, it has to.
And so I've got my expected running time is 1.
It has to output a satisfying argument.
Sorry?
By definition of solving the problem, it has to output a satisfying solution. So you're given a random variable that constructs your instance. Then my question is, what is the expected value of the runtime of an algorithm that provides the valid solution for every possible element that you could provide in your random variable?
So in other words, if I give you an instance that I know is satisfiable, I'm not sure. I don't know the answer to that question. I do know that SAT is a very unusual problem. If you look at, so let's say a SAT instance has clauses. So it has n clauses, and it has n variables. Okay? And let's say this ratio alpha is equal to m over n. Okay? Then it's known that if you look at the space of all possible inputs that have m clauses and n variables, and you pick one at random, okay? Then if alpha is a little bit less than 4.2, then it's going to be satisfiable. And if it's a little bit more than 4.2, it's going to be unsatisfiable. So random SAT is very easy in some sense. Just look at the ratio, and now you know with very high probability it's going to be on the other. That doesn't answer your question, by the way. But I suspect it will have something to do with it.
Okay. Now that's for SAT.
Yeah. We don't know for other problems.
Okay.
Yeah, we don't know for integer programming in general. We just know it's for SAT, because it's a very specific analysis done for SAT. That's why, by the way, in some sense, the SAT problems are easy to solve. So basically, if you think of SAT, right, and I know SAT solvers are very popular, and people use them all the time. If you look at the picture of what SAT looks like with this ratio alpha, what you're saying is that if you think of this y-axis as kind of satisfiable here and unsatisfiable here, right, it looks something like this. All your instances satisfiable, and then whoop, they all become unsatisfiable. And this is the only region right here where the NP completeness actually kicks in. Where you actually have to work hard to find the answer.
Because of decision problem.
Yes. And so that's why SAT is easy in most cases. Because most of the time you're going to be here or here. It's very rare to be in the narrow band. And that's why it's easy on average. The problem with easy on average, or what does it mean to be average, this is a whole area of complexity theory. What does it mean for a problem to be easy on average? What is average case complexity? This is very important, for example, in cryptography. Because in cryptography, it's not enough to have the problem be hard in the worst case. It has to be hard on average. Because otherwise someone will find the one instance where it works and you'll have a problem there. So there's a lot of work there with lattices and sort of finding short vectors and lattices that people have looked at, and I'm not an expert on this, where these kinds of reductions are important. Worst case to average case reductions and so on. So there they have some notion of average case based on maybe sampling the inputs uniformly from the circuit, you can do something.
And that's kind of the essence of my question, is I was wondering, basically, can integer programs be used for cryptography?
Not in general.
Okay.
Because there are some problems there are. So the thing is, the lens of NP hardness is not fine enough to distinguish problems that are good for crypto and problems that are bad for crypto. There are some problems that are NP hard that are very, very brittle in their worst case nature, like SAT for one. Right? Then most of the time you can figure out what's going on. Just every now and then you can't. There are some problems that are just hard in general, and those are the ones that you want for crypto.
So it requires a different kind of reduction.
Yes.
Okay.
So NP hardness is a very crude lens. It's like we've seen with approximations, right? I said that we have a whole collection of problems that are NP hard, but the ability to approximate them changes drastically. You have problems where you can get an arbitrarily good approximation. We saw knapsack. You have problems where you can get a constant factor approximation. We saw vertex cover. We saw problems where the best you can do is log n, which is a number that grows with n but doesn't grow too fast. That's set cover. And we've seen problems that are even worse, like clique or independent set, where you can't get any approximation. And they're all NP hard. So the NP hardness lens is a very crude lens in that sense. It doesn't tell you more interesting things about the nature of these problems. And this is one lens for it.
So what about approximation algorithms for integer programming?
Again, in general, it's not much. You have to know more about the structure of your integer program to be able to say something about, because the actual approximation will depend very heavily on the coefficients and how they relate to each other. It's very hard to say anything in general. Yeah. More questions? From people who may not have asked a question. I'll get back to you if no one else asks. Anyone else? Again, it's sort of a free-flowing discussion today. These are chances to do like a global office hours, I guess. And we also have office hours too. Okay, yes, question.
So regarding my earlier question, so we said that general TSP, if we assume that P is not equal to NP, then we cannot approximate it.
We cannot approximate at all.
Yeah. So if you try to reduce TSP, so you can reduce TSP to IP, I assume. But
Yes.
then what happens when you try to go to the LP? Does it just not formulate?
What happens is that, remember, so this brings up another concept, right? Let me recall this concept of the integrality gap, right? So remember that when we had a picture in our head of what linear programming and integer programming looked like, we had some kind of polytope, and this is the solution for the linear program if this is the direction of improvement. Remember, we can think of any linear program as some kind of direction. You want to go as far in that direction as possible till you leave the safe region, right? And then we also said if you think of what an integer program is, it's really just the same thing, but now I have a grid inside. And my solution has to be one of these grid points. It can't actually be an arbitrary point because I want discrete solutions. And then we said, okay, this is the best integer solution you can get, and that's the best linear solution you can get. Then no matter how clever you are, if you try to solve a linear program, there is some kind of gap between these things. It's going to be hard to reason about none of this. And so the integrality gap for these TSP linear programs ends up being large. There's just fundamentally there's limitation on what you can do. Again, they're not large enough. You can't prove that the gap is huge, but there are some limits on what you can do with these algorithms. And so, for example, you could change the LP. You could say, oh, I want to add some new constraints to my problem to go like this. And now my optimal solution gets a bit closer maybe, if I'm trying to do this very carefully. And people do that. They say, okay, let's take a linear program. It's very bad. The integrality gap is huge. Let's add more constraints to it. And somehow I get closer and closer to the optimal solution. So you can do that. So people have played all kinds of games with linear programs for TSP and other problems. But as I said, I told you earlier when we talked individually, we can prove now that there is no good LP for TSP.
But
At all.
so, if you did try to create an LP from the IP, would it be obvious that there's a large integrality gap? Like,
It's not obvious, you have to prove it.
Okay.
I mean, the proof is usually involves, here is a counterexample. But that can take work. I mean, you can have entire research papers whose entire subject is, here is an integrality gap for this LP. So it's not that simple. Yeah.
So I guess in this process of going from the problem to the LP, you kind of have to reason that your answer actually is.
Or you have to hope that it's close.
Yeah.
Yeah, you have to prove that it's close in some way. That's where the trick comes in, right? So, for example, in vertex cover, we said, okay, just round it if it's more than half. Technically, what we showed was that essentially every answer is either 0 or 1, which is good, or it's half. So it's not integral, but it's half integral. And that's usually a good thing, because if everything is either 0, 1, or half, then you can kind of scale things up, and you don't lose a factor too much. So if all your answers to the linear program are actually grid, but a finer grid, then you can just multiply and get integers. So if all your values are at least 1 over k, then you can scale them up. That's how you can get a k factor problem. There are things like that you can do. So it really depends on the exact problem, its integer program and its linear program. And remember that you can express the same problem in different ways using different linear programs. So that's also a degree of freedom there. If one doesn't work, a different linear program.
And are there problems other than general DSP that are possible to approximate using this scheme?
Using any scheme. I mean, TSP can't be approximated using any scheme.
Yeah.
TSP is the worst. I don't know no natural problem comes to mind. But there are problems that are horribly bad to approximate, like click independent set. Not as bad as TSP, arbitrarily bad, but they're pretty bad. They're like n. You can't get better than a factor n approximation. So if your graph was a clique and your answer was one vertex, that might be the best you can do. So it kind of sucks. Okay, good. So we covered some basics of linear programming, IPs, and we touched on the notion of integrality gap. Any more questions? Yes?
You mentioned with linear programming, we can transform coordinate systems so that we're trying to find a minimum.
Right.
Why was that important? Is that just kind of alluding to how it's solved in practice? Or is there some other important reason to know that?
It's helpful because it says the following. So your general LP, of course, looks like this. Maximize C transpose X, right? What I'm saying is that you might as well pretend that your LP was it's just a way of saying that what's going on in the linear program is geometric in nature and is not as dependent on the actual coordinates as you think it is. That rotation doesn't matter. And if you want it, so there's one algorithm for solving LPs. It's called the simplex algorithm. That's a very popular one. It doesn't run in polynomial time, but it's been used for decades to sort of solve LPs. And it uses this idea that essentially what you want to do is rotate down and then go find the lowest point of one. It's just convenient. So it's a convenient way of thinking about from that. If you see a problem where, I want to get to the bottom of some region, you should be able to recognize, this is just linear programming. So think of it as a good pattern match that allows you to recognize an LP when it's hidden maybe. More questions? Okay. So, you all know about SAT. You probably know about 3-SAT. Yes?
I just have a question first, I was wondering, so if you're given an arbitrary integer program, do there exist algorithms that can tell you the approximation ratio you'll have by relaxing it into a linear program?
No, those algorithms are called people.
Oh. I mean, how difficult is it in general?
Like I said, you can write an entire paper just to prove it. Because what do you need to do, right? So you need to show that you need to construct some instance of a problem that you can construct some instance where there's a little bit of a gap. You want to construct as big a gap as possible. And the question is how you're going to do that.
So the question is sort of, given a universal language of describing problems, what's a way in which you can provide a problem that has the maximum integrality gap, because that gives you your answer.
Right. So there has been some recent research on asking the following question. So we've seen for Max 3 set, and you all did a homework on this, right? That there's a simple algorithm that says just assign variables randomly, and you get some answer. It has expected, its an approximation ratio is 7/8 because you satisfy 7/8 of the clause on average, and that's the best you can do. And that we have an algorithm. There's a line of research that asks the question, when is that the best possible? For what problems is that simple idea, randomly assign things, the best possible you could do? It's a concept called approximation of resistance. And there's been some work on trying to categorize which problems fall into that category. But we don't have an answer that's sufficiently clean that we just put through a calculator and output an answer. But yes, there is an attempt to categorize and classify these things. So in the question you asked me over email, and I was talking about descriptive complexity, there's a whole line of work in saying, just like we did with LPs, where I said, if I can express it in this form, I have a solution for it. There's a whole line of work that says, if I can express my problem in a certain language, can I press a button and then immediately know what the complexity of the problem is? And it turns out you can do that. You can say, for example, a problem is in NP if and only if you can write it in a certain fragment of logic. A problem is in P if and only if you can write it in a certain fragment of logic. And if you can't, then it's not in P. So it's, we don't, that's the problem. We don't know if you can't write it or not. And even at a more basic level, there are these things called constraint satisfaction problems, where you can say, if you have a certain number of constraints and a certain number of variables of constraints, this problem is going to be NP hard, otherwise it's going to be easy to solve. And so on. So there are attempts at systematizing, just by looking at a problem, how hard it is, which is kind of cool. Because you're saying that the hardness of the problem is inside it somewhere, it's encoded in its description. And it's not based on your ability to think about it. But we're not fully there yet. We have a lot of partial results along these lines. We're not quite there in terms of answering the question. Okay, so I wanted to take another example and maybe have you do a little. So we've seen SAT, we've seen 3 SAT. You may have heard of 2 SAT. In 2 SAT, again, you have clauses and variables, but there are 2 variables per clause, not 3. So we know that 3 SAT is NP complete. We also know that max 3 SAT is NP complete, which kind of follows, right? Because if 3 SAT is NP complete, there's no way max 3 SAT can be polynomial. You see why? So if 3 SAT is NP complete, which is, check if there's a satisfying instance, then max 3 SAT, which is satisfy as many clauses as possible, has to be NP complete as well. Because if this could be solved, then I could just run this algorithm that claims to solve it, check if the answer is all the clauses or not, and decide the answer to that question. So this NP complete means this NP complete. Now, 2 SAT, where you only have 2 variables per clause, is in P. I don't know if you do this already, but this is kind of a cool little fact. So going from 2 to 3 is what makes all the difference. Max 2 SAT, for which we can no longer apply the same reasoning, is in fact NP complete. So 2 SAT is not NP complete. It's polynomial time. But max 2 SAT is NP complete. Okay, max 2 SAT is NP complete. It must have an integer program. You have 5 minutes. Write an integer program for max 2 SAT. So again, I have clauses, C1 through Cm. Each clause consists of 2 variables. So you can think of each individual here as y1 and y2, and so on and so forth. Write down an integer program, and the goal is to satisfy as many of the clauses as possible. Write an integer program to solve max 2 SAT. Okay, 5 minutes. Again, you can talk amongst yourselves. Take it. Yes?
Are there only 2 variables that I can throw all clauses?
No. There are n variables in general. So there are n variables. So let me give you an example. This is what a max 2 SAT instance might look like. So I have n variables, x1 through xn. So let's say I know. So I'll set something. So my first clause might be x1 or not x2. That's my first clause. My second clause might be x2 or x3. My third clause might be x4 and not x1. So in this case, I have 3 clauses. and I have 4 variables. Okay, this is an example of using some max to set. I have variables, I have clauses, and I have some set rules, and they're always true in each. Yeah. So like with any problem, you want to think about, okay, what are my variables? What is my objective function? That's usually a good place to start. What's your objective function? How do I encode that linearly? And then figure out what the constraints on the variables need to be, and how to encode them linearly. Question of the day. Write an issue program for next to set. Okay, any questions so far? Any thoughts, any observations, you're stuck, you have no idea where to start? These are also good questions to ask. Okay, who would like to propose an objective function? Anyone? Any candidates for objective function?
Maps the sum of the clause variable. You have variables for clauses.
So first, you have a variable for a clause, we'll call it CI. Okay?
We want to maximize the sum of them.
We want to maximize the sum of the clause variables. And the intended encoding is that the clause variable will be set to 1 if the clause is somewhat satisfied. Good. That's the first step. We have a clause variable and we want to maximize the sum of these clause variables, with the intention being that the clause variable is 1 if the clause is satisfied. What next? So any questions? Did everyone get to this point? I mean, this is the objective function you want to. So you want to think of having a clause variable. You want to maximize the sum of them. Okay, I should put a sum here, but. Okay. All right. You want to carry on?
That's right.
That's very good. Okay, very good. So now the next question is: okay, I have these clause variables. They have to be set to 1 if the clause is satisfied. Do I need more variables? What more variables do I need? I need variables for the actual things to be, the literals to be satisfied. So I have the variables xi, 1 for each variable, right? Okay. So now we have clause variables ci, we have actual variables xi. So we need to somehow make sure magically that the ci is set to 1 if it's satisfied. And we know that xi is set to 1 means xi is true, and xi is set to 0 means it's false. How can we ensure that? That's a constraint now. We set up a linear constraint that makes sure that this never gets set to 0 if they're both 1. How would we do that? Yes?
Well, we can first say that ci is less than or equal to 1.
Okay.
And we can say that it's
So we'll say
That
ci
makes
is
sure
less than or equal to 1. Oh, sorry, less than or equal to 1. Yeah?
And then you can also say ci is less than or equal to the sum of its xi's that are part of it.
So the proposal is that so let's say a clause I, the clause I, consists of x1 or x2. Let's say this is our example, right? So the claim is we will write for this clause the constraint ci is less than or equal to x1 plus x2. That's the proposed constraint. And so you write that all for all the clauses now. And then you're done. Thoughts? Sound like a good idea? Bad idea? Horrible idea? Nice. So I guess the question is, how can you tell if it's a good idea or not, right? It's one thing to say it's a good idea, but how do you even tell? Well, you can try putting in some values and seeing if things work. Right? So what do you want to have happen? In this particular case, if these two are both 1, you want this to be 1, right? So you're going to put, so if these two are both 1, this thing becomes ci should be less than or equal to 2. Since you're maximizing, you might as well, increase it like that.
That's why there's the other inequality to make sure that it's bounded by 1.
So you want to put
We
this
don't
and that.
we don't want to double count the clause, right?
You don't want to double count a clause. Very good. So you have this one and this one to make sure there's less than or equal to 2, but it can't be more than 1. So all you can do is push it up to 1. Right? If either of them is 0, this sum will be 1. In which case your now constraint says ci should be less than or equal to 1, which is also fine because you'll get up to 1. If you're going to maximize, it's going to push up to 1. And if they're both 0, this will be 0. And so it can't be anything else. It has to be 0. Because we have the positivity constraint in general. Another way you could do this is to say, well, actually what I want, I'll remove all this, I'll just say, look, ci belongs to 0, 1. Right? That'll take care of all that problem. I don't have to worry about this. What about if my clause consisted of x1 or not x3? How do I write this clause now? Now what do I do?
1 minus x3.
Tell me what the inequality will look like. Cj in this case.
Cj less than or equal to x1 plus 1 minus x3.
Right? You see the 1 minus because you're just flipping a 0 to 1. Sorry?
Machine learning.
There you go, machine learning. It in some strange way, it saddens me that you use machine learning to learn algorithms. I prefer to do the other way around.
Well, no.
Just kidding. So, don't tell the lyrics. So this is good. So we have now a way to encode every single clause in my problem. We just write them all down. And we have an integer program. The integer program is going to basically look like max sum of ci such that for all clauses, so for all ci equal to xi or xj, Ci is less than or equal to xi plus xj, and correspondingly for the other cases, come all down, and Ci and xi belong to 0, come all down. So we have a valid integer program. You got a question on that, Daniel?
Oh, I got it.
Is this clear? So we've gone from max2 set to an integer program. And of course we can make it linear just by covering something. So again, let's check. We have a linear objective function. We have linear constraints. And once you have linear constraints, we know that we can always make it in the correct canonical form. That's usually easy to do, whether it's equality or not. That's not, yes?
Just instead of writing 1 minus x3, we can denote it by x3 prime, which is complement of x3. And still my inequality looks like the same. Ci is less than equals to x at less than.
Right, but then you need to add the extra equality that x3 prime is equal to 1 minus x3. Sure, you can do that too. That adds more constraints and more variables to your problem. That may not be a good thing. Or it might be a good thing, it depends. But yes, that's an example of saying you can change the nature of your LP. You don't have to have a single answer. This is perfectly valid. So again, what he was saying was that you don't have to have separate cases. You could just say, you know, if there's a negation, put xj bar, xj prime, and if it's not negated, just put xj, then have a whole bunch of equality constraints that make sure that if one is 1, the other one is 0. Which again, you're allowed to do in an LP, because we can replace equality constraints by inequality constraints. Yep, that's fine. Okay, so now that we have an IP, which we can relax to an LP, we also have a sense of how we might go about solving this problem. Right? We've seen this with max3 set as well. You just pick variables at random and you can just set them to 1. And you can show that with some probability you will satisfy how many? So if I pick variables at random in a 2-set problem, and I set them to 1, what is the expected number of clauses I will satisfy? Which you might be able to do off the top of your head. What is the probability of not satisfying a clause? How many cases? So how many cases are there for the values in a clause? There are 2 variables, so there are 4 cases, right? Each of them is 0 or 1 with some, each of them is 0 or 1. Out of those 4 cases, only 1 case will make the clause unsatisfied if they're both 0. All the other cases will make it satisfied. The probability of not satisfying that clause is 1/4. So on average, you'll satisfy 3/4 of the total of fraction, 3/4 fraction of all the clauses. That's your approximation ratio right there. 3/4, you're done. Okay. So this is again a simple example of how you take a problem, map it to an integer program, and again an LP if you wish to sort of think about that way. You could also then solve the LP. You'll get fractional values for these things, and you can try to round them. You can say, okay, I'm going to get fractional values. Based on the fractional value, I will round the problem. Right? You have to be careful in your rounding because you don't want, if these are all fractional, you want to make sure that when you round them, you don't make this inequality unsatisfied. You don't make this infeasible. But you can do that. That's another way you can think about solving this problem. Okay? All right. So that's just a bit of practice in how to take a problem and convert it to an IP. Let's do a little bit more practice. So we've all seen the problem of matching. You're given a graph, and you want to find a subset of the edges such that all edges in M are disjoint and the size of M is maximum. Right? Maximum matching is find a collection of edges that don't overlap that are maximum. Okay? All right. Write an LP for this, or IP for this. Go. How would you write an integer program for matching? The wrong angle to read it. So again, you got to think about matching pictorially. It looks like this. You have some graph. Some form. And a matching would look like, oh, I took this edge, and I took this edge, and then I took this edge. They're disjoint, all the edges, they don't touch each other. And at this point, I don't know if this is maximum, but it's definitely maximum. I can't add anything else to this. So write an IP for this problem. Yep.
So I looked on the max 2 set, so we were saying that our IP was a 3/4 approximation?
No, I said that you can get a 3/4 approximation to max set just by randomly assigning values to be 0 or 1. If you actually use the LP, you might be able to, actually I don't think you're really better, but you might be able to be a bit more clever about what the wrong is. Okay, but I'm just saying this small we can do, you know, something to 0, 1 people problem.
The problem with that in the program is that the optimal solution is set all like signs of 1/2.
Yeah, that's correct.
So,
But that's what the rounding is going to do, right? So if you set all except 1/2, let's say to randomized rounding,
right,
the probability of setting it to 1 is half, which is exactly what the solution we said was the solution.
right.
So the LP is giving you a guide as to what to do. It's just not very useful. Again, these are the variables, think of the objective function first, and then start working backwards to try and build constraints and make sure the variables in the objective do what they need to do. Everything is similar to everything. Well, so you learn match law. What? Matching can be improved. So in some form, so it's similar. Yeah. But I won't do it directly. Because this graph may not be mathematical, which is your flow mode. Okay, any proposals for objective function? For maximum matching?
Each edge times 1, where edges are 0 or 1, there are variables for each edge.
Okay, so it sounds like you're saying I want to maximize the XE, where XE is a variable that will be 1 if you pick that edge to be in the matching. Is that right? Okay, good. So now, we could just pick every edge, but we can't. There's a reason we can't pick every edge. How do we encode that constraint in linear fashion? The constraint, of course, is, I don't want two edges to overlap. So, yes? You want to get it? Ian?
Oh, okay. So XE and XF, where E and F are edges that should be disjoint because they share an edge, you have the constraint XE plus XF less than or equal to 1.
Suppose I have another one. Suppose I have edge G.
All of them share the same vertex.
Okay, so good. So what you're saying is we have one constraint for every vertex now, that you don't, the total sum of all the edges you pick coming out of it must be at most 1. So for all V, right, the sum over E equal to, I'm going to write this in shorthand as V star, just to indicate all edges coming out of V. There's no direction here. XE is less than equal to 1. Okay? And of course XE belongs to 0. Do we have any other constraints? Or is that it?
I think this is sufficient too, because you would just consider every pair, so for example, if you consider first, second, first, and third, second, third,
Right.
then you would have the same constraint.
How many constraints would you have?
More,
That's what.
but it'd still be polynomial.
Yes, you're absolutely right. It is a valid LP, it will work. But I want to write this more concise LP because I have a devious ulterior motive in mind, which will become clear in a minute. But you're correct. That original one you stated for every pair of edges, add them up, it should be 1, is correct. It will give you a correct answer. So in fact, let me just emphasize it by writing it down. For all E comma F, XE plus XF less than or equal to 1, where E and F share a vertex, is a correct formulation of this integer program. It's absolutely wrong. You're going to have, in the worst case, you could have n cubed constraints, which is not great, but still, it's polynomial. Okay. All right. So let's stick with this for now. Okay. We have this IP for matching. Let us make it an LP by the enormously difficult task of this. And now that it's an LP, let's write its dual, which was the devious ulterior motive I had. It's easy to write a dual for this LP. Now remember, and again, there is no way, I'll be very impressed, frankly, if anyone can do this in their head. I can't do this in my head, but I cheated when I practiced today morning, so I do not do this in my head, but only for this one. So remember, this one looks like max C transpose X AX less than or equal to B. If that's the case, the dual needs to look like min Y transpose B, Y transpose A greater than or equal to C. I have to put these transposes to make sure I'm not mixing up row vectors and column vectors, but you get the basic idea. Right? So we somehow need to take this problem, map it into this generic language to figure out what C, A and B are, and then plug that into the other side, just like we did. It turns out this case is a little bit easy because this is just a whole bunch of ones. Right? This is also a whole bunch of ones. So this is going to be Y transpose B. Now what are the Y's? These are dual variables. Remember we said there's one dual variable for every primal constraint. What are the primal constraints? These are vertex constraints. There's one constraint for every vertex. So there must be one dual variable for every vertex. Let's call it YV. So if you look at this, we're going to get something like minimize summation YV for all B. Because B is all ones. Right? Y transpose B is the sum of all Y's. Sorry, this is hard to see in front, isn't it? So, Y transpose B is sum of all Y's. And so far so good. We've got this annoying matrix to deal with now, but I don't know how to do that, so we'll figure that next. Now if you look at the matrix, I'm not going to write out the whole matrix, but what's happening is that we're saying that if you wrote it in this form, every row of your matrix is going to be a vertex. That's why you have one constraint for every vertex. Every column is going to be an edge. So if you visualize what this matrix, one row of this matrix is going to look like, and I'm going to write it up here, it's going to see for the vertex V, it's going to have a 1 and a 1 and a 1 and a 1 for all the edges adjacent to it. Because you're going to add up all those edges. Right? Because you have this matrix, you're going to take the first row multiplied by the column of x's, and you're going to pick up only the ones that are relevant to the vertex, which are the ones that's adjacent to it. So that's what that matrix is going to look like. Right? So it's a vertex edge matrix where you have ones for all those things. If you think of that now, and if you now say, okay, now I'm doing Y transpose A. For every vertex, I'm going to pick up the two endpoints of an edge. If edges are variables in the primal, edges are constraints in the dual. And it's going to look like this. For all E, you add up those two things. So for all E equal to U comma V, YU plus YV is greater than or equal to C, which is a 1. And you're done. This is what our dual looks like. The dual LP. Let me now add in some integrality constraints to get an IP. What is this problem? This problem has a name. It's a very familiar problem to you. Just stare at it a bit. I have a graph and a bunch of vertices. I want to minimize the sum of the vertices which is picked, which is 0, 1, subject to this constraint for every edge. What does this problem look like?
Edge cover?
Sorry?
I mean, vertex cover?
Vertex cover. This is vertex cover. Why? I want to minimize the number of vertices I pick with the constraint that every edge has at least one endpoint. So what is this weird picture telling us? This weird picture is telling us, it's telling us this very interesting fact. Something that is called, I believe, Konig's theorem, if I'm not mistaken. If you take maximum matching, and you take vertex cover, and you write down its LP, and you write down this LP, these are duals. If you didn't have the language of LP duality, it would be a lot harder to see this. You could still do it. This is what Konig had proved. But it's not easy to see this without this connection. That in the linear relaxation, they are duals of each other. They are the same problem. It's just that in the integer versions they're different. And they're hugely different. Max matching is solvable in polynomial time. It was in fact one of the first polynomial time problems. Vertex cover is NP hard. But the LPs are duals of each other. This in some ways is a good thing, right? If I take the vertex cover LP, find its dual, I can solve it optimally, easily, without, I don't solve any LP, but I can do this actually very easily. And then use it to somehow solve my vertex cover, which is what we've done in the past. So linear programming allows you to establish these kinds of connections. Sometimes directly, but sometimes via the dual. And again, we've seen other examples with max flow, for example. So we've seen the example I'm going to write at the bottom here. Max flow is here, which has its own LP, which is dual to another LP, which gives you min cut. But here, both these problems are solved in polynomial time, because the integer solutions are the linear solutions. The linear relaxation gives you an integer solution. It's a very special case. So these two problems, which are integer problems, have linear relaxations which are identical in terms of the optimal solution, and they're the same. Here, two problems that are quite different in complexity, polynomial time versus NP hard, have the same linear relaxation. And that's what linear programming gives you, all these connections. Questions? Yeah.
Would it have been really a lot harder if we had gone with the Ian's constraint?
I smell a homework problem. What would have happened? We would have had one constraint for every pair of edges. So you'd have one dual variable for every pair of edges. And I'm not good enough at writing LP duals to tell you exactly what that dual would look like. But it would be interesting to write it down. It would be a lot. I suspect what will happen eventually is if you simplified it by looking at the dual very carefully, you would end up with this. But it may not be obvious. And that's why choosing the right kind of LP can often be a bit of an art. If you choose a wrong LP in constructor's dual, it gets messy. Like for example, I've told you about how you can get rid of equality constraints and greater than equal to constraints just by remapping things so you can get the canonical form. That's true, but when you actually do LP dual constructions, you don't want to do that. Because you get all these extra variables because of all these extra constraints, and you actually want to collapse them. And there's a standard way to say an equality constraint corresponds to a variable that could be positive or negative. A greater than equal to constraint corresponds to a variable that's negative. A less than equal to constraint corresponds to a variable that's positive. There's a whole bunch of rules of all this, which makes it easier to actually write the dual. So these all are the same thing, but choosing the right form of the LP can make writing the dual a lot simpler sometimes. So that's where the art comes in. Sorry, cookie cutter. Yes?
So if a problem can be solved in polynomial time, does that mean that the LP will be equivalent to the IP?
We don't know that. We know the converse of that. If the LP is equivalent to the integer program, if the LP is integral solutions, then yes, the problem can be solved in polynomial time because the linear program can be solved in polynomial time. We don't know the converse. We don't know if it's true for every problem in P that it's LP, because this may not be true. For example, a problem admits many LPs. One of them might be such that the LP has the same solution, has integral solutions. Another one might not. Right? So it depends on the LP you pick for the problem. So I've given you now a couple of examples of how to take a problem and map it to an LP. And this is, there's again, an ulterior motive here is that these are some of the questions I'm going to try and ask you to work out for yourself when I give you the homework. So think of this as kind of a practice where you want to think in a somewhat organized way. Oh, I have an objective, figure out the objective, get the variables, then figure out how to make the variables be the way I want them to be by setting up constraints properly and make sure everything is linear. And that's pretty much how every construction is going to work. Okay? Other questions? Yes?
Can you clarify the mapping between the language that we used initially to express the LP and then the canonical language?
This?
Yeah.
Oh, okay. I mean, how do I convert arbitrary constraints to this form?
Yeah.
So this part is usually always the same. It's some linear function of the input. Now you might be minimizing instead of maximizing, in which case you just put a minus sign. That's easy. Right? And again, geometrically speaking, if I minimize it to maximize, I'm just flipping everything around. Doesn't change the problem. So it should not. That's fine. Now we've said that we always want something less than equal to some constant. Sometimes you may not have that. So one thing I said was that if you have a constraint that looks like, x1 plus x2 must be greater than or equal to 5, right? You can rewrite it as minus x1 minus x2 is less than or equal to minus 5, which is basically minus 1 times x1 plus minus 1 times x2 is less than or equal to minus 5, and now you're back in the standard form that we said we need to be in. Right? That's for grid equality constraints. For equality constraints, if you said that, x1 plus x3 is equal to 7, well, that has to mean that x1 plus x3 is less than or equal to 7, which I can handle. And it also means that x1 plus x3 is greater than or equal to 7, which I can now handle. And then this can be converted again to that. So you get the constraint minus x1 minus x3 less than or equal to minus 7, and now you're done. So these simple transformations allow you to convert any problem into this canonical form. But effectively what happens is that we said that every primal constraint becomes a dual variable, yes. But this kind of primal constraint becomes a dual variable that's less than or equal to 0 all the time. This kind of constraint becomes a dual variable that could be anything. It could be more than 0, it could be less than 0. That's what basically happens. So we didn't talk much about semi-definite programs. Right? And something you should pay attention to. They are, like I said, very useful. And they give us this scope to go beyond what an LP can do for us. For example, for max2sat, the problem we just talked about, you can write out a semi-definite program, much like the way you write out a linear program. But you have to write it somewhat more carefully. And you can then solve it the same way you solve a semi-definite program. You find these vectors and you round them like in the hyperplane, and you can get a reasonable answer. And so again, the thing I want to emphasize with semi-definite programs as opposed to linear programs is the way to think about them. And again, this helps you sort of do some pattern matching here. So we said that a semi-definite program looks like the following. Again, it's like a linear program. You want to maximize some linear function of the input, but now my input is a matrix of variables, not just a vector of variables. So I'm going to write this in this form, where this means take every value of this matrix, multiply by every corresponding value of this matrix, and add them all up. It's like a gigantic inner product of two matrices. And then you have a whole bunch of constraints of the form a, k, x less than equal to bk. Right? So a whole bunch of constraints of this kind. Where again, you should think of this as some dot, it's like a dot product, but it's, of course it's over a matrix. And then finally, you have this non-linear constraint that this matrix is positive semi-definite. Right? And the way we thought about positive semi-definiteness was that it was the matrix equivalent of being greater than or equal to 0. That's all its eigenvalues are greater than or equal to 0. And for any such matrix, you can think of it, any matrix of this form can be thought of as really being in the form y transpose y. Okay? So you have a bunch of vectors in a dot product with a bunch of other vectors. And if you think of x equal to y transpose y, then xij is going to be the inner product of yi and yj. Always. This is how matrix multiplication works. Okay? What that means is that if you read all these expressions, what you're saying is that you're doing something that we'll call vector programming, essentially. Namely that what you're saying is you want to maximize a sum of Cij xi, yi, comma yj, right? Subject to constraints of the form, I don't know, sigma aijk, yi, comma yj is less than or equal to some bk, right? And then you have these other constraints. So if you're taking machine learning, you may have come across kernels, and this thing called the kernel trick. If you haven't, you will eventually. And the basic idea is if you have a problem that's non-linear, but the only way you're interacting with the problem is through these inner products, it's sort of morally speaking linear, just in a higher dimensional space. And that's the sense in which semi-definite programs are a generalization of linear programs. You're doing what we call vector programming. Instead of these being scalars or vectors, and you're only interacting with them through the inner products of this kind. And so that, what's surprising and not obvious is that you can still solve this problem in polynomial time, up to any desired approximation. But what's also cool is that it gives you more power. Because again, to draw our example of the linear program, your linear program was sort of sharp and pointy, right? These are the constraints, but with the semi-definite program, is intuitively you can get this kind of curved constraint here. So you can kind of get closer to your integer solutions. So you can often do better than what the linear program would give you. And that's the main intuition. I don't expect you to become experts in semi-definite programming by the end of this class. We just did one lecture, but this is the intuition you should carry away, that there is a way to write something more generally than the linear program. It's not as easy to tell. So I said, it's very easy to tell you can write something in linear programming form, just write it. It's not as obvious to do it for semi-definite programs. It takes a bit more work. You have to think a lot harder. But if you can, there's a payoff for doing so, as we saw with max search. That you can do much better than the half approximation by doing this max, writing this SDP in the rounding. There are many deeper reasons why SDPs are interesting here, but I won't get them here. If you wait till next semester, we have a new professor coming in who will be teaching a class, an advanced class on optimization, and he'll cover some of these things. So I've said this before, that the basic message of optimization is at some level, convexity is your friend. Right? So if you have a problem so if you have a problem where you want to optimize a function that's convex, the picture you should have in your head is a big U shape. So I have some function, I have something that looks like this. This is what a convex function always looks like. Right? There's one base level. And you want to minimize. So you got it going down. The one here. This in some sense captures easy problems, or problems that we can actually solve in problem. Because of the way the convex function is, and there's some technical details, but the way the convex function is, there's only one solution. And if you just keep going down, using greedy or whatever you want, you will eventually find it. The key is the eventually part. And you have to prove that you can do this eventually fast enough. But that's the basic idea. If your problem has this kind of structure, which is convex, a convex structure, then you should be able to solve it in polynomial up to some desired degree. Okay? And so everything we do within P starts off with simple things, like I said, with linear programming, and it goes out to semi-definite programming, and there are sort of larger classes here, till you finally get a general convex program. All of these problems, if you get expression problems form, you can solve it for them. Of course, the annoying thing is that P looks like it could be bigger than this. This doesn't capture everything we can solve. There are problems called, there's something called submodel optimization, which is kind of outside the space, but you can still do something. There's some nonlinear problems where you can get an answer. Again, doesn't fall in this category. But this is a very large class of problems where you can solve things efficiently. And so, if someone gives you a problem and you say, okay, can I solve this problem? The first thing you have to test is, can I write it in linear form? Can I write it in semi-definite form? Can I write it in some convex form? Is it a convex optimization? And if you can, then there's hope of doing something clever. If not, then you have to work hard. It's most likely to be NP hard. An NP problem in your mind should look something like this. Lots of local min. One global min somewhere. Maybe even many global mins. But a much more complex landscape of the cost function. Where it's hard to figure out whether, when you're here, it's hard to figure out that, oh, in fact, if I jumped up a little bit, I could get further down. Or if I jumped up a little bit more, I could get even further down. It doesn't work. And that's in some sense what makes these problems hard. But there's so many little bumps here, you don't know which is the right one. So next week, I want to start talking about a little bit about big data problems. Because as we've seen already with our study of approximation randomization, dealing with large data, and that wasn't the only reason we studied them, but they made understanding these issues much more important, to the point where there's really no choice but to be approximate and be randomized. And so I want to talk about some surprising things you can show with data that's large and lives in high dimensions that are counterintuitive and are not what you'd expect, but are in some sense good news for dealing with large data. And again, they're fundamentally algorithmic in nature. They change the way you think about these problems. So we're going to talk about that for a while. Okay? All right. Yeah, that's it for today. I will see some of you in office hours, and I'll see you all next week.
Just wait for 1 minute. We will start. You can just ask me. I'm sitting right next to you. It's very clear.